that I was going to study the partition function of this object as a function of inverse temperature. Phi naught is going to be a parameter that is appearing here through the combination of these g and lambda over there. And this partition function was the partition sum that I wrote like this, of E minus beta f of phi and phi naught. I'm not writing the explicit dependence on lambda because it's not going to play much of a role in the behavior of the system. So I'm putting together g and lambda, if you wish, divided by lambda. In both cases, lambda is not going to be important. But the ratio between the two it is. So notice that differently from what you usually do when you think about Ginzburg-Landau sort of pictures, as I started saying in the first lecture, where I said that at high temperature, the free energy f of phi looked like this, at the critical temperature was flat, and then had the double well structure. Here I'm fixing this form, the one with the two wells. G is positive, so this term here is negative explicitly, and beta appears as usual in a partition sum as the prefactor accompanying what is like the Hamiltonian of the problem, that in this case is this function null f. Okay, until this point we arrived last time, and next what I said was that this problem, in the limit of large n components, many components, n going to infinity, can be solved by using a trick. There are different ways of implementing this trick, but I did it in the simplest possible one, I think, which is to propose that the 5/4 term, which is the one that renders this Hamiltonian non-quadratic, I'm going to decouple in a product. Yes. Sorry? Before I rescale, should it be? No, the root n I keep it separately. The root n is here. This one I keep it.
Right. So when I solve that with phi naught.
Yes. Okay, but yes, that's true. That's true. Okay, and this is okay. You're right. These are the minima. Let me write it like this because I want to keep no n in the definition of phi naught. So these are the minima for this equals to 1. And I perfectly agree with you that if I took this form of f of phi, the minima would be located in a position that depends on calligraphic n. But I don't want to define phi naught in this way. I want to define it this way because this is what is going to be important next. Okay, so let me propose this kind of factorization. And next, see whether it's feasible, whether it leads to a solution that makes sense. Something I didn't stress the other day, and might have led to confusion because, okay, I didn't detail the calculation sufficiently well, but it's also very important to be able to carry on this calculation, is that I should remember that here, in 5/4, there is an R dependence, right? All these phi's here depend on R, and then I have to integrate over space. So here, there is an R dependence, and here, there is an R dependence. But there is no reason to believe that once I separated my 5/4 term in two terms, in two factors, and one of these is an average, there is no reason to believe a priori that this average will depend on R. What I'm going to assume, again, which is a second assumption, and at the end of my calculations check that this is correct, is to say that this 5/4 phi squared x average doesn't depend on the position. So no dependence on R of first factor. And if it doesn't depend on the position, I can, for example, evaluate it at r equals to 0. It's a position like any other one. I have to keep the r dependence in the second factor. Or I can evaluate it on average over the space if I normalize correctly. So let me put it like this. The x pi squared x of r factor pi squared of r. Or I can evaluate it in any other position. Yes? A potential that would depend on? A V of R. Well, it depends. It depends what is your V of R and how you scale it with N. And there are also tricks that you can do for other potentials which are not necessarily 5/4 a power law. Yeah. No, but there are things that you can do. Even you can do similar things if your potential is quench disorder. It's a bit more complicated. But you can do Gaussian approximations that amount to what I'm doing here, but self-consistent Gaussian approximations. So in the end of these Gaussian approximations, you have to fix the two-point function, which is what I'm going to do next. And everything closes, and it works fine. But it's slightly more complicated. Okay, so this is the trick. This is the first step of the trick. This is the second step of the trick. Once I have done this trick, imagine that here I replace this term in this form. You see that the f became now quadratic. F became a Gaussian weight, if you wish. It's a quadratic function of phi. But it's not a Gaussian theory that I'm using, so this has to be well understood. A Gaussian theory would be something where I had a term like, I don't know, let me call it mu f squared with mu a constant. Just some external parameter, some constant. Here, the presence of this constraint in the quadratic part of the potential is going to be very non-trivial. It will have very, very non-trivial consequences. And actually, this model was one of the first models that showed that you could have non-trivial exponents at a critical transition explicitly. So it was one of the first old models that were solved exactly, because it can be solved in all details. And it's one of the models that is discussed in the Baxter book. So here's a reference, exactly solved models in StatMech from 82, I think. But okay, this problem had been solved much before this date. And it has non-trivial exponents at the transition, so it's exponents that are not, just 1 or 2. So how goes next the calculation? I'm not going to do it in full detail because otherwise I could spend all my lesson on the statics of this problem, and I want to go to the dynamics. So let me just give you some little explanation of how you can find the equation for the correlation length that I showed the other day, very quickly at the end of the talk. So the way it goes is the following. So it's better to work in Fourier space. So once you have your f being quadratic, you can go to Fourier. Yes? Sorry? No, for n going to infinity, of course. No, as soon as you want to put... As soon as you want to include 1 over n corrections or go beyond that, it's very, very difficult, of course. If you put n equals to 2 and you are in 2 dimensions, then you go down to the XY model. I will say some words about that, which can be solved until some points, let's say. It cannot be solved fully, but can be quite solved. And n equals 3, again, you can say things about it, but you cannot solve them exactly. But the answer is not in 3 dimensions. Yeah, yeah. So, okay, so n equals infinity is important here. N equals 1 is the easy model in a sense. Yes. So, okay, so you go to Fourier, and if you go to Fourier, what you find for the way in which you can rewrite your f with a little bit of calculations, and let me put proportionals, not to put the 2 pi's, and so on. I will write it like this. So if you go to the Fourier space, the quadratic form, you can diagonalize it, semi-diagonalize it in this way, with a kernel here that has the k-squared and has an extra term that it's like a mass in field theory terms, and that I'm calling psi x minus 2. And this psi x minus 2, you can read it directly from the other expression over there, will be given by, if I didn't make mistakes, put the 1/2 over there. And this is a 0 in real space, right? It's r equals 0. Okay? So you can read it right from here after the factorization. And next, what you need to find is an expression for this one. Okay, is what is missing. But an expression for this one, you can get it using this action. I'm calling it action, Hamiltonian, free energy. I'm using all these names because they are used in different contexts, but whatever is the weight of the configurations of the field phi. So this one you can compute it using this weight. And if you do, I leave it as an exercise, then you will find that this is given by the expression that I gave you the other day. So it's given by this. Where I wrote it in terms of a discrete sum over wave vectors because it's convenient in this problem to keep a finite volume and follow the dependence of all the correlations and so on, and the critical point and the correlation length, as I said the other day, with the volume. Okay? So this is the expression by putting the model in a box, volume D. Okay, once you are here, you have a self-consistent equation for psi x. And this self-consistent equation, okay, I'm not going to solve it here. The only thing I want to say is that this equation has solutions. And the solutions it has, well, they will lead to a critical temperature. And you can characterize this critical temperature. I gave the expressions, I think, the other day. It is not very important. It has an equation that fixes it. The point is that there is a critical temperature here. And this critical temperature will depend on, sorry, phi naught and the dimensions of phase. If you study a little bit the dependence on the dimensions of phase, you find that there is a upper critical dimension, which is 4. And next, in the following, I will focus on d smaller than 4. Okay. And details on how to, continue this calculation and fill in all the holes that are very simple. I mean, apart from solving this equation, that might be a little bit more complicated. The rest you can find in this book. Or you can find also in, the notes that I'm going to give to the organizers, but basically there's a paper which has a long summary on this. Yes? This is for n going to infinity, yeah. It's for n going to infinity. N disappeared from the game. And it disappeared from the game thanks to having done this approximation here, because otherwise it wouldn't be. That wouldn't be true. Okay, so around 2002. Okay, but this is just to give you a flavor of how this problem is treated at the static level and how a transition temperature is found, and which is the trick. I wanted to stress this trick. Now what I want to do is to do the same trick, but at the level of the dynamics. So I want to start from a phenomenological Langevin equation for this field with a force, deterministic force in this Langevin equation determined by this functional f, and noise. And what I want to see is what happens with the stochastic evolution of this problem. So let me erase here. I will erase also here. Make some space. So, the Langevin equation, I have already written it down the other day, I think. Write it like this. So this is the noise. This is what I call the deterministic force. This is the term that originates from viscosity, or friction, let's say. And I dropped the inertia, so I dropped the second time derivative term that might be there, but for this problem it's not going to be important, so I can drop. I mean the overdamped limit. Yes? Physically, okay. There is a very nice proof of the Langevin equation that consists in doing the following assumption. Assume that you have your system, so your field theory, if you wish, and you couple it to an ensemble of oscillators. So this means that each degree of freedom of your system, you couple to an ensemble of oscillators. So for instance, in this problem, this could be something like saying that I'm going to couple my field to a sum of, so let me see how I write it, Cn, Xn, sum over n, from 1 to some other number here that I don't want to call n. So this is a coupling between the coordinates of the oscillators. The field, I have to scale in some intelligent way this coupling constant. But then I will have in my total Hamiltonian this coupling plus the Hamiltonian of the oscillator, so H of oscillator. So this problem can be solved. What do I mean by this? The dynamics of the oscillators can be solved because the oscillators by definition are harmonic. So they are harmonic oscillators. So if you write down the Newton's equations for this problem, for the field are for the oscillators. You solve for the oscillators, you introduce back into the equations of Newton for the field, you will find that these equations gain 2 extra terms. These 2 extra terms you can identify with the noise and the friction. You can identify them with noise and friction when you take a limit of having many, many oscillators. So this number going to infinity. For each degree of freedom, you have an infinity of oscillators coupled to it. And then the characteristics of the noise and the viscosity, if you wish, the friction, what you have here, whether it's white or it's not white, and things like this, you can tune by the distribution of the frequencies of the oscillators. You have to move all your oscillators with you, if you wish. Yes. Yes. Of course, in the Brownian motion vision, you can identify it better because you have a particle with a fluid, and then you see the friction as the resistance of the fluid to the motion of the particle. But this is much more general than that. So there is a justification of the Langevin equation from this modeling that goes well beyond having a particle in a liquid that can go. This is one of the reasons why you can use these sort of equations and don't make mistakes. I mean, the fact that these kind of equations describe the motion of the dynamics of many systems that have nothing to do with Brownian motion. Yes? Yes. You have to choose it in a special way. It's an ohmic distribution. The spectral function, it goes like a power 1 of the frequency. But if you choose another one, you will get color noise with some correlation function, a kernel that characterizes the memory of the noise. Yes, exactly. It's a classical version of Caldeira-Leggett, which was done by Kawasaki and by Schwanziger before, but I'm sure that other people did it also. I mean, it's exactly the classical version of Caldeira-Leggett. Okay, so here we are. So now, if I look at this term, in this term I will have nabla squared, if I compute it explicitly, of the field, which comes from the first one, and then I will have plus G, let me see that I don't make mistakes, P alpha R of t minus lambda for goes n, and here I will have phi, let me see, phi squared, I will have phi alpha, so this is of r again, this is of r, of t, and let me put the good factor, or at least the one I'm using in my notes. Okay, no, something. Okay, let me do it slightly differently to keep the notation I have in the notes, and I have. This is not wrong, but I just want to do it slightly different. So let's look at this term here before. So that term here I'm going to rewrite in a convenient way. So the way in which I will rewrite it, and I'll let you check that I don't make mistakes here, is that I'm going to write it as is what I call f of phi. I'm going to write it as lambda over 4 phi squared minus phi 0 squared, there is the n here, minus lambda phi naught squared over 4. Okay, it's just a rewriting of this thing, missing a squared, of course, of this object over there, where I made explicit the dependence on phi naught. I took the lambda out of this factor, this term, and then here there is a constant. Okay. So this constant is irrelevant with respect to the dynamics, so it will not contribute, so I can forget it. And now I have the f of phi written in a more convenient way. That is the one that I'm using in my notes. Good. So now, if I do that and I take the derivatives, I will find this thing here. No lambda because I set it to 1. Thank you. Because it's just an overall constant here and it won't change anything. So I just set it to 1.
And the G got it,
the G is here. Exactly. So I remember that phi naught is defined here. Okay, so what do I see here? I'm still writing in terms of fields, vectors. So I see that this term is linear in phi. This term is the noise. There is one term here which is linear in phi. There is one term that is not. This. So it's the same situation that I had before at the static level, only now I have time dependencies. And these are important. I have a time dependence that I want to stress. Here, here, but especially here. I have space and dependence. I also have it here. So I want to do the same trick that I did before. Only that now my phi 4 my phi squared, sorry, depends on two variables, the space and time. So the naive assumption would be to say that I replace this by the average, and I don't keep neither the dependence on R nor the dependence on T. But that would be wrong. I mean, if I do that, it's an assumption. I do it, I go and check whether I find a solution consistent with this assumption, I won't find it. What I realize is that I can drop the R dependence, but I cannot drop the time dependence. So don't drop it. So
your initial model, there was only R.
at the beginning, I had only R here in what is like the Hamiltonian, if you will. But next, I included dynamics into the problem through the Langevin equation. So now I have time as well. So this is the evolution. This is the what dictates how the field evolves in time. So now I have both. And here, when I want to copy what I did before, if I copy it too naively, I would make a mistake. This, of course, you can realize only if you do it, and then you realize that you made a mistake. But I'm going to do it directly, correctly. And what I'm going to do is the following. So let me see it. I'm going to define a tilde of R and T 1 over n phi squared of R and T. And I'm going to say, this here comes the assumption, that this R tilde doesn't depend on R, since I'm going to replace this thing by 1 over n sum over alpha phi alpha squared of R T initial conditions and noise. Okay, so I'm going to replace this object by an average. Now it's not an average over the partition function, it's an average over the noise. And I'm going to include as well an average over the initial condition. And this makes me think that I haven't defined the initial conditions yet. So let me give, I'm going to raise here, make some space. Yes? Yes, exactly. So this could be included through initial conditions or through some field that you put somewhere. Exactly. But now I'm going to say that my initial conditions are going to be typical of a high temperature situation because I want to consider a quench. So then I'm going to say that my initial conditions, the phi vector of R at time 0, are going to be taken from a PDF, probability distribution function, Gaussian, let's say. And I'm going to say that they have 0 mean. So I'm using these square brackets to note the average over this probability distribution, and that they are beta correlated in a way that introduces some parameter, delta. And here I could choose different kinds of correlation functions. I could choose delta correlation functions in space, or I could give it some width, not to work with something which is going probably to bring me some divergences. So I can put some cutoff, as I said that was necessary last time, and well, regularize a little bit this delta function. Short distance cutoff. That I'm calling lambda. Yes. Exactly. I'm starting close to here with fluctuations, which corresponds to saying that I started from a disordered initial condition, which is like saying that I was in equilibrium at some temperature, let's say, and then I quench. Yes. But I'll compute correlations. And the correlations will be non-trivial. But the average also tells you some interesting features that I will discuss later. Okay, so now the question is, how do I compute this A tilde? And the calculation goes along the same lines of what we have done for the static. Actually, what one has to do is to notice that once I replace this pi4 term in the way by factorize, and as I did, what one finds, so replacing A tilde in the Langevin equation, you will find that the components of the field decouple. And this is very easy to see, because the only place where they could couple was through this thing here. And I have made it quadratic now in the field. And I have introduced this as an external parameter that I have to fix at the end. But there is, once I work with this A tilde, I have no more information about the phi alpha within it. So the components decouple. And if I write down the equation, which I'll write it down here because it's the thing with which I will work, is A tilde phi 0 squared. Let me put the signs correctly. Let me read it from there. So it's phi naught squared minus A. Okay, so now I have an equation that I can solve. This equation, I can solve it easily if I go to Fourier once again. So if you Fourier in space, I get d phi of k t dt equals to minus k squared plus a of t that multiplies phi of kt plus psi of k and t. So what you notice here is that for each mode k, this Langevin equation is like a harmonic oscillator with a mass, with a, well, spring constant, let me call it instead of a mass, which is equal to k squared minus a of t. So I don't know if you remember the equation for a harmonic oscillator, but okay, I can write it down. The potential of the harmonic oscillator is k, the spring constant, so let me call it spring constant here, x squared over 2. So the force is obviously minus k spring constant x. So in the Langevin equation, this is the part that will enter the deterministic force. So it's something linear in the variable, x, in the case of the harmonic oscillator, with a prefactor, which is this spring constant. Here I have the same thing, but my spring constant depends on time. And this is the fact that gives the non-triviality to the problem. If it were independent of time, well, it would be a harmonic oscillator. The only thing that the field could do is, if the harmonic oscillator was, pointing upwards, its potential, then the only thing it could do is to move in there, no special interesting dynamics there. If it were unstable, well, it will flow to infinity, again, no special interesting dynamics. But the fact that it depends on time will make it non-trivial. No, it's no. The only thing that the noise term gives for the harmonic oscillator is just fluctuations, but fluctuations around the mean, the bottom of the well, so around the equilibrium position at 0 temperature. The fluctuations, nothing else. Yes, something will happen, exactly. So there will be a time that will move that change, it makes the sign of this factor change. And this will give you information about the problem, or will determine the behavior of each mode, of course. So this equation can be solved. It's still a linear equation, so one can solve it. And the solution looks like this. You can check it explicitly if you don't believe me. Okay, so there is this time-dependent harmonic constant here that will appear in an exponential integrated. And now, what you can do is, for instance, you can study what happens with the average of this field. Yes? In Newton. But here I'm in Langevin. So all the acceleration, I dropped it. I could have kept it. It only makes the calculations more complicated, but it doesn't add anything special. So I can look at the behavior of this quantity on average over the noise. If I average over the noise, well, this term doesn't depend on the noise. This term does. When I take the average, since the average of the noise is 0, the second term, which looks complicated, I can drop. And I keep this one here. And I have the impression that it will fall off to 0 exponentially for all modes, which are positive here. But as you said, I have to be careful with this other term. So I need to know what is A to conclude about the behavior of the modes and to say something else on the problem. Now, how do I fix A? Well, I have to fix it by its own definition. So I have to go up here. Here, I have an equation that is the same for all the alphas. So actually, I could have erased here the 1 over n, the sum over alpha, and the alpha, and use it for the solution of this equation. I have the solution to the equation, so I can Fourier transform back to space and do the average over the noise and the initial conditions, and I will get a self-consistent equation for A. Like what we did for the statics, only that the equation is different. So I'll write it down. I don't do all these steps, but you can do them. I mean, you can just have to plug in this solution in there and do the averaging. Yes? Yes, you could. Because you will have to say something about the typicality of this thing. So if you are a mathematician, they prefer to work in these terms. Don't do the average and start saying things about, typicality of one configuration of the field or of the spin. It's the same. I mean, it doesn't change. So the equation for A, I didn't write it, of course. Did I write it? No, I didn't. It will be an integral equation, which looks a little bit complicated. We will have things like A of t equals 2, and then a functional here with integrals of A of t prime. Well, it looks a little bit awful. But you can solve it. At least you can relatively easily extract the asymptotic behavior of A of t. And you can even solve it exactly numerically and get the full dependence and so on and so forth. What is important is the asymptotic behavior of the A of t, actually. So the asymptotic behavior of the A of t is different if you're working at temperatures which are above the critical temperature that we found with the static calculation, the critical temperature, or below the critical temperature. Yes? Yes. No, because for this kind of initial conditions, you will find initial conditions which are 0 on average and that have some with their correlation in space, but not that much. they will be enhanced, but they will be enhanced to do the coarsening features, to do the coarsening phenomenon. But it won't affect A. What will affect A is if you take an initial condition that is, say, I don't know, positive field on half of your volume and negative field on half of the other, on the other half. That is very special initial condition. It's not typical. You introduce the order already in your initial condition. Some information about the ordering where you're going to go. You see? Or if you introduce bands in your initial condition. So then, of course, this is a very peculiar initial condition that involves some knowledge from your side of, where is the system going to go. Yes, yes. Yeah. It's an initial step, yes. It's to consider certain protocols. By choosing these initial conditions, I'm choosing one type of protocol, which is implicitly quenching from high temperatures to somewhere else, either high temperatures still or low temperatures. But if I want to introduce some information about the equilibrium properties of my problem at the temperature at which I want to work, then I will have to choose different initial conditions, and then the equation for A will be different, and it will tell you something else.
They also
Yes. No, this is not in this problem. No, it doesn't happen. Of course, other nonlinear equations can lead you to these sort of features, but not this one. Yeah.
But also it becomes easier because you're the large.
Because I'm in the large limit. Yes. Otherwise, there are certain features that don't survive, including 1/n corrections, but some generic ones do. Yes, I agree, but it's again the thing that, thinking about the particle on top of the hill for this problem is tricky, because you have all the channel that gets out of this blackboard and has a lot of space to explore. Yeah. What is? Calculating A. Yes, this is what I'm going to say. Exactly. So what I find out is different behaviors, and I'll tell you which ones. Let me summarize the behaviors for A that will determine the behavior of the dynamics. I'll do it here. Erase this thing. So, A. T larger than Tc, T equals to Tc, T smaller than Tc. So above Tc, A goes to a constant. And this constant is just the equilibrium correlation length minus 2, not surprisingly. If this thing goes to that constant, maybe with the opposite sign, yes. Opposite sign there. No, it's okay, sorry. It's okay. Because, yeah. So if this thing goes to k squared plus psi x minus 2, then I'm sure that the dynamics of the field will go to equilibrium at the, as dictated by this propagator, if you think in terms of what's going on with the field theory, right? K squared plus psi x minus 2 was exactly the combination that I had in the quadratic Hamiltonian that I start with. So this is not interesting. I will find exponential relaxation of correlation functions, nothing very special, but it's consistent with expectations. Now, if you take t equals to Tc and you solve that equation, what you will find is that A of t goes to 0 asymptotically, with a prefactor here that depends on dimensionality, which is important. You don't see it from here, but it is important, the value of this prefactor. But for the moment, let me stress that it goes to 0. And if I go below Tc, it also goes to 0 with a different prefactor as 1/t. So if I come here and I look at this expression, I notice that if this thing goes to 0 at very long times, it's only this one that remains. So if k is positive, non-zero, strictly positive, then I'll also have some kind of harmonic oscillator for each of the components of the field. This one makes it decay, and there's no mystery, nothing special going on. But for k equals to 0, both terms go to 0. This term vanishes. This prefactor vanishes. And next, what I have is not a harmonic potential. I have a random walk. If I don't have a potential, then I have a random walk. Diffusion. So in the limit of long times, and this is the key point, t much longer than some microscopic timescale, the k equals 0 mode diffuses. And this is at Tc and below Tc. The way in which it does is different, but both of them tend to diffuse. And the fact that they tend to diffuse, what is telling you? Well, it's telling you that the k equals 0 mode is already telling you that the k equals 0 mode is the one that's going to grow in the problem, while all the other ones will tend to disappear. And this you see it from this solution. Imagine that I don't average over initial conditions, but I average over the noise, so I kill the second term. If some microscopic timescale that, it's hidden within my Langevin dynamics, has to do with the friction and so on. Just long time. This first term is the only one that remains after averaging over the noise. And I see that if a of t goes like 1 over t, the integral of 1 over t will go like a log. The log in the exponential will give me a power law. And the power law will be determined by the prefactor here or there. Okay? So I will have a power law dependence on top of this exponential here. But this exponential here, for k equals to 0, is not there, so I only keep the power law. So it's very peculiar at the k equal to 0 mode in this sense. This, if I look at what is the, for instance, let's see, at t minus tc, t is smaller than tc, I mentioned some kind of Bose-Einstein condensation features the other day. So what's going on here? If I look at how the 0 mode behaves in time, well, it's the initial condition that it's over there. I'm not averaging over it. And then I have t to the d, over 4. Where is the 4 coming from? Because I forgot a 4 here. Yes, I had forgotten a 4 here. So it's d over 4. So it's growing, you see? Growing in time. So the dynamics is such that this 0 mode does grow in time. But if you remember, and if you do the calculations till the end, of the static properties of this problem, you will see that the 0 mode in the static configuration has an average that goes with the volume of the sample. So this thing is tending to do what it has to do in equilibrium, but it will never reach that volume dependence for finite times. So what this means, let me finish the phrase. So what this means is that this mode is growing. This is order. The k equals 0 mode means that everything wants to be the same. But it will grow in time, but it doesn't really reach the equilibrium situation, which is every single piece of the sample covered by this order in times that do not diverge with the volume, because I need something that diverges with the volume to reach it. Yes? Yes, all these things you can compute here. Exactly. So this, for the moment, I only talked about this condensation phenomenon and time-dependent condensation phenomenon of the 0 mode. Now, all the scaling I discussed in the last lecture was extracted from the correlation function, so was applied to the correlation function. You can compute all the correlation functions. Now that you have, the field, you compute it, and what you find is the following. So let me summarize. This is again exercise. So they are very easy, all these calculations. They are a bit lengthy, but they are extremely easy. So what you will find, for instance, let me see, at TC. At TC you will find that this correlation function, let me see which one I wrote here. Well, I wrote the most general one. Initial conditions, noise. So this correlation function will behave as phi naught squared r, let me call it x and y, and r will be x minus y. So r minus 2 minus, there is a function of t over tw here, and there is an exponential, there is a t over r squared to the 1 minus d over 2, and there is an exponential of minus r squared over 4 t plus 11. Okay, so this is the ending expression for the space and time correlation function. I put different points in space, different points in time. It's just from plugging in the solution into the averages.
This is the sum limit of T minus.
No, this is general.
Oh, yeah.
This is completely general. So, no, exactly. No. I don't. I don't have to have relativity here. So what I read exactly from here, the fact that I have an r squared over time, is that if I want to write this term, let me look at it at t equals to tw to make it simpler. So at that particular values of times, I have r squared over 8 t. So remember the scaling I was discussing the other day. I have to have a function of r over r of t, well, in this case, a squared. I want this thing to be a function of a ratio between a length and a length. So what I read from here is that the length goes like square root of t, the dynamic length. If you want to match the unities, the dimensions, you may have a constant, but I'm working on units such that length and times have the same dimensions, and then I forgot it. Yes. Exactly. It was divided away, the friction constant. Yeah. This one? No, it's t. Is the total time. This is the total time. T minus t waiting is the difference. So this is t waiting. This is total time t, both measured from 0. Exactly. Yes. Yes, it does. It does, exactly. It is telling you that the domains are growing. They're growing in time with the power law, and then when you extract this typical length, what you find is 1/2. It's boring as a result. What do I say? Why do I say that? Well, what is boring is that the ZX that I got there is 2 in this case, and it's not 2.13 or whatever. But okay, this is what it is. What is interesting from this result is that you get all the scaling features that I showed to you the other day are included in this expression. So here I looked at the particular case where t is equal to t waiting, and I extracted the r critical of time. But I could have also looked at this prefactor here. Remember that in the scaling I said that the scaling of this kind of correlation function should be a function, I don't remember how I called it, but a function of an r of 2 minus d minus eta. So this tells you that eta is equal to 0 for this model, which is consistent with all the calculations of equilibrium correlation functions at the critical point that you can make. So for this particular model, the anomalous exponent eta is 0, and the equilibrium dynamic exponent is 2. But this is boring in the sense that these are boring exponents or boring values, but the framework is correct. The framework is realized. By the model. And this is nice, because you have an exactly solvable model where you can see all these features appear. Yes?
What kind of small external
Yes.
to make the people model?
Yes.
Would you still take a sign that's
No. If you take a finite field and you apply it to the field, to your phi, you will very quickly project your sample into the ordering. If you take an infinitesimal field and you scale it with the size of the system and n in this case, then it will take long to go. But if it's finite, then that's boring as a procedure, if you wish. It's like pushing this thing away from there, from the maximum, and boom, it will fall. Yes. 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 This form is a peculiarity of the model. This Gaussian thing is a peculiarity of the Gaussianity of the model that you have from the start. This, absolutely. So this you don't get with this model. Remember that I said that the general form was this R to the minus, well, something like this, times a function of, if I stay at equal times, a function of, R over RC of t. Now, this scaling function is something which is very difficult to compute for problems which are not like this one, which is solvable, for problems which are more realistic. And the features are very sensitive. I mean, you can change them by changing model, and this is not universal. I mean, this is what I mean. The features of this scaling function, well, are a scaling function. So. Yeah, you still get that, yes. Yeah, no, it's not, you're not going to cure it in that way. So, yes? Yes. Yeah, but if you can do it in Fokker-Planck, but you don't gain simplicity of calculation, let's say. Yeah, no, not in this problem. Not in this problem. Yeah. Exactly, but in this problem it's more difficult. In diffusion problems it's not. It's better to do it in Fokker-Planck usually. But for this sort of problems it's better to work with Langevin. Yes. Yes, you can learn things, of course. You can learn things about the gap, you can estimate the equilibration time from looking at the gap of the excitations of the Fokker-Planck operator, or a la Schrödinger, and all these sort of things can be done, but I don't think you gain much more information than looking like this. Yeah. Yes? Sorry? Yes. Where can I find it? Okay, you can find it in this paper of Corberi, Lipielon, Zanetti. There's a lot of details there. Less details, and only for the low temperature phase, I think, are in Alan Bray's review. So there's this is a very nice review, 95, I think, more or less. It's mostly, it has a big part which deals with trying to find intelligent ways of computing these scaling functions. And he summarizes all the techniques that are in the market, or that were in the market in 95, but there are not so many new ones. None of them works very well. I mean, certain aspects they do, some other ones they don't. But he was interested in that features at the time. The A of t, you can find it in this Corberi paper with much more details. Okay, so I could also show you which is the scaling form for this problem below the critical temperature. I'm not going to do it because it's a long expression. The point is that it satisfies all the properties that I told you about last time. Let me just say that ZD is also 2. And this means that at low temperatures, the domains grow like t to the 1/2 as well in this problem, which is not the case in other problems. In other problems, ZD remains, for instance, in Ising model. Yes. No. This is for t less than Tc as well. This is for, here was 2 Tc. I wrote an expression for A. I said how A decays when T is less than Tc. So it's like D over 4T. And then I said that the mode, the zero mode, condenses with the power law below Tc. That's what I said before. Now I was talking about correlation functions to extract the growing length. Okay, so just stress here that the Ising model also has ZD equals to 2, but ZX is different, and it depends on dimensionality, and it's slightly larger than 2. A bit larger than. This is important for what I want to say next, because I'm going to stop discussing this ON model now, and I will try to discuss with you a bit briefly yes. Say it again. So, T equal to Tc, yes? Yes. 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 It's because the critical dimension, the upper critical dimension for the problem is 4. Yeah. This is the dynamic exponent that characterizes the growth of equilibrated patches at Tc. So this is at Tc. Is the one that characterizes the equilibrated patches below Tc. So let me put it like this. So what's above the line is below Tc, and this is at Tc. Okay, so what I want to do next is to revisit these Kibble-Zurek arguments and tell you that for these problems that are coupled to a bath, that do have dissipation, that do have domain growth of this kind, at least the naive way in which the statement is made is wrong. Okay, so I want to insist upon that. This one here, this one is numerical and RG calculation. At the critical point you can do. Between the numerics and the... There is little differences. There is little differences here. But it's always very small. Like, I don't know, in the second digit. So, KC procedure, let's say. So I don't have a lot of time, so I will be brief in this part. Usually, a picture like this is drawn, where here you have your control parameter. Here is the transition. For me, the control parameter is temperature. And this is the equilibrium correlation length, which diverges with some power law at the critical point, right? And what people say, which is definitely true, is that if you now, instead of very rapidly cooling by a quench your sample, you do an annealing procedure, so something like that looks like this. So this is the control parameter. That for me is temperature. This is time. This is the level of the critical temperature. This is 0 time. So this is positive time. This is negative time in the convention. And that you change your temperature in a linear way. So you do something like this, for instance. Then what you will find by this slow cooling, if you just so Q to be slow, is that the system will follow this line in the sense that it will have equilibrated patches of the length of the correlation length, roughly speaking, up to a certain point, and that then it will block. And at the moment at which it blocks depends on the value of tau q, and it will block later in the sense that for a value of psi which is higher, if you do it more slowly, and so on and so forth. So I fully agree with this first part, which is definitely true. With what I don't agree with this part here, and with this part here. Why so? Because I have argued for 2 days now and a half that if you do an infinitely rapid quench, either to the critical point or below the critical point, the system does not block. It continues to evolve. It continues to evolve by growing these structures, which are either the equilibrium patches at the critical points or the domains, which are more nicely looking, below the critical point. So there is no blocking. Not even for a quench in my language, which means infinite rapid cooling. Okay? So if there is no blocking for an infinite rapid cooling, it will not be another blocking, or it will not be blocking either, for a slow cooling. I don't know. I mean, I cannot understand it. I mean, the argument for these kind of problems cannot apply. No way.
Yeah, there is no force.
Probably he didn't think about coarsening. You may have another view.
So the equation at extra length is
Which is non-trivial.
it's non-trivial, but if you use extra length, well, you can get like perfect.
No, but with extra length. But you have to take into account the extra length.
Yeah, but that's people say that it's worth about people doing their project work. But if
Yes.
you say that the rate of cooling is like speed.
Yes.
So you can say speed at scaling dimension, and one of which is at scaling dimension of heat.
Mm-hmm.
So you can say that you have a two variables at scaling dimension, one of which is like in any case, the stick is everything works perfectly.
Yeah, but it's not the way in which it's written down. The way in which it's written down is that it blocks here and it blocks there, and this is not true. What the length will do, if now I think about, I call R the length of my structures, the length of my structures will have this length here, I agree, and then it will continue growing when I enter here, and then I will continue growing while I'm in the critical region. Let me write it like this. It will grow with RC of t. When I'm away from the critical region, it will grow with R of t. These two are different. So this goes like t to the 1 over z dec, as I said. This goes like t to the 1 over zd. And if you want to measure how the length that gives rise to the density of defects, the density of domain walls in my problem, depends on tau q, you will find, say that you want to measure here, at some temperature t star, then you will find, I don't know, this value for this tau q, another value for the other one, and so on and so forth. And what people tell you is to compare, is to have a look at the density of domain walls. Okay, show it now here. Yes? There are two values of the cooling rate that you use to go through the phase transition. So say that this is tau q1. This corresponds to tau q1. This corresponds to tau q2. And so on and so forth. So here you're going more slowly than here through the phase transition. Okay? And imagine that in my plot, I say that I want to measure at some given temperature T star. Well, I want to measure here, I want to measure there. I want to measure here for another tau q and see what is the number of domain walls. Interfaces are. if I do this, did I switch it on? Yeah. Yeah, I'll take it down. That's what I derived for RC of t here, R of t there. I do the matching between the two. This can be done when I go through out of the critical region and within the lower critical region. So low temperatures, critical temperatures. And I look at how this R of t crosses over from one to the other, and what does this imply for the number of defects, number of domain walls. The idea is to say that the number of defects will go like 1 over the RD that you have at the time that you want to look at. But there are two dependencies here. There is the time that you want to look at, but there is also the cooling rate with which you went through the transition. So there are two parameter dependencies there. But to simplify life, let's look at T equals to tau q. So this is number of defects 1 over RD at tau q. If I stay at T equals to tau q, you see that here I stay at temperature 0. For this problem, I have no difficulty in going to until temperature 0. It's a classical problem. So this T star is temperature 0 in my plot. T star equals to 0. Okay? And if I analyze how these are depends on time and temperature, something that I haven't discussed until now. Until now, I only talked about the time dependence of the growing length. I was not saying anything about the temperature dependence of the growing length. There is a temperature dependence of the growing length in the low temperature phase. In the critical phase, there is no need to discuss it because I am at the critical point, so the temperature is equal to Tc. But if I go below the critical point, well, I have a full range of temperatures to consider. And indeed, one can also prove in these problems that the R of T below the critical temperature is a function of temperature times this power law. Okay, so the time appears like the power law that I have already mentioned, and there is a prefactor here that depends on temperature. And one can characterize this prefactor. The dependence on temperature of this prefactor actually is something that decreases to 0 at Tc. This one. And then you have to do the matching when you approach the critical region. You have to do the matching between this one and that one. Okay? So from that matching, you extract how this one decreases to 0 at Tc. This can be done, and I can give you a reference if you wish. Anyway, so once you have established this form below Tc with the temperature dependence, and the other one that you already had at Tc without temperature dependence, if you do an extra assumption, which is to say that when temperature will depend on time, I will be able to replace temperature as a function of time within this prefactor, which is non-trivial assumption, but more or less we checked it. If you do that, okay, you put everything together, you replace in here, and you find that for this problem in particular, with all the exponents that are known, for the 2D Ising model that I'm looking at in this picture, the density of defects at this tau q goes like n to the tau q to the minus 1. Okay? And if you used the exponent that Kibel-Surek tell you, or the argument tells you here, you will get a value which is 0.31, I think, something like this, 0.3, minus 0.3. So this one is much smaller than the other one. If you don't want to call it Kibel-Surek, let's call it blocking. Okay, and this is the important thing is that this one is much smaller than that. Yes? Yes. Exactly. Absolutely. This is what I'm saying. This is exactly what I'm saying. It's not what I read in most papers. But no, it's not what I read in most papers. In most papers, in many papers, I see people measuring here. Many people measure here. Some of Zurich's papers as well. And this is not true. I mean, this is just my point. Of course, that the scaling they have for this point is perfectly correct. No question about it. It's only that you have to add the further evolution that you have at the critical point, which turns out not to be very important, but below the critical point, certainly. Okay, so this is just what I wanted to say very quickly about Kibble-Zurek. I wanted to show you, but I don't have time, but I will do it very quickly, some applications of these ideas to problems which are of interest right now. I mean, because from my talk, perhaps you could have thought that all these features are physics of the 60s, and who cares? I mean, we should go beyond that. Yes. Yes. It's in the expression that I'm not giving to you. There is new within. Yes. There is new, there is ZDEC, there is ZD. And for the special case of the 2D sync model, where I know all these exponents, I replace, and I end up having -1. But, but they're all in it. Yeah, exactly. It's just equilibrium. That's what you get here. Yeah. Okay, so just very quickly, in 5 minutes, I want to show you one problem which is of interest right now, which is this problem of artificial magnets. So let me just go quickly and tell you what they are. It's not moving. Sorry? A little bit, yes. So these are arrays of little magnets. So you have to see here a square lattice. A square lattice where they are on the link. This is link. A little magnet is sitting on top of the link. Here there is another one, there's another one, another one. So they are building a square lattice, but they could build any other kind of lattice with these little magnets, which actually they're not so little. So they're kind of macroscopic objects, which are like this, arranged in vertices, in this case, of coordination 4. And the other thing that you have to see in this plot is that there is black and white, white and black. So this means which is the orientation of your magnet at this particular configuration. So imagine that I say that white and black means an arrow pointing up. So the magnet is oriented in this direction on this link. On the horizontal is like this, here is like that, and here is like this. Okay? So this is the pink vertex. And if you now think in terms of arrows, you see that the vertical arrows are antiferromagnetically oriented. They point in opposite directions, and the horizontal arrows as well. So this is like an antiferromagnetic local order in the horizontal and vertical directions. Okay. Next, if you look at the yellow one, you will see that there are 3 arrows pointing in and 1 pointing out. Or the opposite. I don't remember which convention I used before. In any case, there are 3 white dots close to the vertex and only one out of it. So this is like a 3 in, 1 out vertex. 3 arrows point in, 1 points out. And this one is in the blackboard, because I think I changed convention while I was talking. So let's see. Let me write my convention. So 3 in, so white, black, like this, and yes, exactly. I have to reverse. So white is up, white is in, and white is down. So here is white, and so on and so forth. So this is for the pink. For the this one is 3 in, 1 out, and this is 2 in, 2 out. So that's the blue is 2 like this and 2 like this. So it's like a ferromagnetic vertex in the sense that they're oriented in the same direction horizontally and vertically. Okay, so it's not difficult to imagine that there are 16 possible vertices that you can construct. And if you look at the experimental realizations that these people are doing, it turns out that if you count the vertices, you will see that there are more of antiferromagnetic ordering than the other ones. And this is because of the kind of lattice lattice spacing that they used in their construction. You can argue, you can compute why this is so, that the antiferromagnetic vertices are energetically favorable in this situation. Yes? Well, next the question is what you can do with these vertices. Can you freely turn around an arrow or not? Then you have to know something about the dynamics of your problem, right? Because there are models of this kind that have been known since the 70s where you allow for certain kinds of vertices only. So there are an ensemble of problems which are called vertex models where you allow only for vertices which don't have 3 in, 1 out, or 3 out, 1 in, and don't have, which there's none in any case in the picture, 4 out or 4 in. So there are ensembles of models that have been studied in the statistical physics community for very long, where you only allow for, say, this antiferromagnetic, this ferromagnetic, and the disorder case where you will have something like this. I don't know, none of the two. So I don't know, something like, is this a good example? Anyway, all the, let's say, 2 out possibilities. This is what is called the 6-vertex model. So if you are in this context, then you cannot flip freely an arrow because you will break the constraints. If you flip an arrow, you won't get 1 2 in, 2 out vertex. You will get something else. You get out of the definition of your problem. Now, in this context, in the experimental context, this is not the case. You have thermal fluctuations, you can break the constraints, you can have all kinds of vertices, the 16 kinds of vertices. Only that, for energetic reasons, these are more favorable than the ferromagnetic ones, than these ones, and than the other kinds of effects. The ones with 4 gates. This is what we are, sorry. Yes, exactly. No, it's not. There are symmetries, yes. You can pair your vertices. Okay, I have it in a transparency. Here's the all the vertices that you can have. So you can have ferromagnetic vertices like this. This is the rotated of that one in the sense of more than rotated is the inverse. I inverse each of the arrows. This is another kind of ferromagnetic vertex, and this is the inverse of that one. This is antiferromagnetic, and its inverse, 4 in, 4 out, and the other 8 cases where I have 3 legs of one kind and 1 of the other one. So these are all the vertices that you have. Now, these people, let me go quickly. Okay, these models, as I said, have been studied when there are no defects. The phase diagrams are known. The phase diagram have very nice features. There is a disordered phase that for this kind of model, the 6-vertex model, is of 2D XY model kind, is critical. This phase is critical in that case. It is not anymore if you add the other vertices. There are ferromagnetic phases, there's antiferromagnetic phase. There's a lot of richness in the phase diagram. And since there is a lot of richness, it's very rich, this phase diagram, I could imagine preparing my sample here, say, in the disordered phase. These are the parameters, scale, way, doesn't matter for you now, that control the weights, statistical weights of the different vertices. Doesn't matter. This is a phase diagram. I can put my system initially in the disordered phase, and I can, in principle, take it to the ferromagnetic phase or take it to the antiferromagnetic phase and see what happens. For the experiment that I showed you, the relevant region of parameters is along this line. It's going from the disorder to the antiferromagnetic phase. But you can cook up other lattices or other, in different tricks, with different tricks, where you can also reach this to ferromagnetic phases. So this is a problem where you can do quenches in many senses, okay? And you could go from disordered phase, from a disordered phase to different kinds of ordered phase, through phase transitions, which are quite peculiar as well. So you can, use everything that I discussed before to try to understand the evolution of these magnets. Well, I won't go into the details of this. Let me just jump over and tell you, for example, what one can see. So one can start a situation in which, from a situation in which your system is disordered. So different colors correspond to different kinds of vertices. So the pink are the antiferromagnetic ones, the blue are the ferromagnetic ones, if I remember correctly. Anyway, there's just, some code for a disordered configuration here. Now, if you let it evolve in contact with a thermal bath, like doing Monte Carlo dynamics, for instance, what you will see is that the system will evolve after a quench into the antiferromagnetic phase, into a situation that looks like this. This is a typical configuration at a given time after the quench, where you have the pink region here, where you have staggered order of antiferromagnetic kind. So all this island, which is pink, is antiferromagnetic order. But then there are boundaries. And in the boundaries sit the other kinds of vertices, which are not antiferromagnetic. And we can understand, why these boundaries tend to be diagonal. We can understand a lot of things. This is a dynamic configuration. An equilibrium configuration looks a little bit more like that. It's more of a sea of antiferromagnetic order and defects because of thermal fluctuations, as in the easing problem that I was discussing. Now, the experimentalists prepare these samples, and what they want to know is whether they equilibrate to some ensemble of, the same kind of questions that we are asking here. Whether with their procedure, when they get something like this, and this is a picture of their configurations, with this kind of grayish region with antiferromagnetic order, and the other dots being vertices of other kinds, they want to know whether this configuration can be a typical configuration of equilibrium at some temperature. Is it that or not? A little bit like Edwards sort of thing, what happens in granular matter. And what we can say from our understanding of what's going on is that if I compare this configuration that they have to a dynamic one or to an equilibrium one, well, it looks more like this one. This one has walls, this one also has walls. While an equilibrium configuration doesn't have any walls. It has fluctuations, but not extended objects of different kind within. So, okay, this is just to tell you that these ideas of coarsening processes that were not taken into account until now in this context, as far as I know, should be useful to try to understand what they want to know, which is whether they equilibrated their samples or not. No, but they do. No, the things are big. But what this experimental group does is that they grow, as you do in granular matter, they grow their magnets in time. So at the beginning, temperature is relevant. At the end, it is not. And again, a la Edwards, they want to know whether the block state is thermal in some sense or not. And from our point of view, it looks more like what you would get with a normal coarsening until some time. Okay, so this is time enough for me to stop here. Just let me conclude by saying that I discussed things which are very standard. I mean, my first two lectures are extremely standard. You have this Bray review, you have my lecture notes that I will give him, this paper by Corberi and company for the ON model. I forgot to say that that same group studied distributions of work in the form of distributions of energy exchange with the bath by the system during coarsening. And they have lots of very nice scaling functions for this object here. And it's not fully understood what they get, but for the ON model, they can compute everything you want about this. And you see, this during coarsening depends on T and TW, because the delta that they are computing is h of t minus h of tw, if you wish. It's the energy of the system at time t, the energy of the system at minus the energy of the system at time tw. So this depends on the two times and the value that you want to look in your distribution. Right? So, so many things that can be done. They did the ON. They had done before the Ising case, but there, okay, it was not. They didn't really understand what was going on. Then they went to the ON. And the ON is more under control. They have a very nice phase transition anyway. I mean, there are very nice things, features going on in this distribution here. So that was something I wanted to say. Another thing I wanted to say is that all the ON calculation I've done can be done quantum mechanically as well. So the extension to quantum mechanics of the ON model can be done, calculations can be done. You can find an R of t that goes like t to 1/2 as well. There are many things that could be said here about this problem becoming classical or not. Okay, I didn't have time to discuss it, but it's something that is possible to be studied. Okay, I think I will stop here. Yes. Yes, exactly. That is something else that I forgot to say. So, in XY type models, you know that there is the Kostelis-Thouless phase transition, and then you can start from a disordered initial condition, very high temperatures, quench below. So the calculations can be done in the spin wave approximation where you neglect vortices, and there what you find is that R of t, there is an R of t, everything scales as in a critical situation because the low t phase is critical, the full low t phase is critical. So, and you find a 1/2 there in the spin wave approximation. This by looking at the correlation functions of the cosine, for instance, of the vector. Now, if you include vortices, there are arguments which are a little bit hand-waving. There's checks which are numerical that suggest that you gain a 1/log correction, a log to this thing here. And this thing was argued by Alan again some time ago. And then we did some simulations with Asia more recently, where this thing is seen very clearly. And there were also numerical results by Hughes before that got the log there. Yeah. For the O3? O3 sigma model, yes. Again, Alan has arguments, and numerically it was done by Japanese guy whose name I don't remember, but yeah, he did the O3. There is nice because there you have lines of effects, and he has a wonderful dynamical, program and graphic thing that shows you how these lines combine or open up, and they do all sorts of amusing stuff. Yeah.
I'm not so surprised by like doing scripted rows by doing
Absolutely. Yes.
And it's very right to get a lot of them.
Yes.
Usually done by a local.
Yes, and doing it. No, I absolutely agree. No, I don't think they tried that. They're pretty recent, these experiments. They're from last year. And so this is a group in the UK. There's a huge collaboration on these problems in the UK. And then there is another group in Los Alamos, and they're doing a different kind of procedure. They're doing more like shaking. They apply a field, and they oscillate this magnetic field, different directions with different frequencies and so on. And then they see which kind of configuration they get at the end. And again, they check equilibration or not of the ending configurations they obtain. Yeah. Thank you. I was wondering what it was. Thank you. I saw it there. I said, what is this? Thank you very much.